So in this video, we're going to, from a graph, figure out where a function is increasing, decreasing, concave up, concave down, and then we're going to look for any relative extrema and any possible inflection points. So increasing, decreasing, let's do those first. So if we read a graph from left to right, it's increasing if it's going up. So it stops increasing right about there, and then it decreases to about right here, and then it increases. Now we write up our answers in interval notation. Now we can't see the graph past here, but we're going to assume that this behavior keeps on unless we're told otherwise. So we can see that it's increasing from negative infinity, and we always do interval notation is just the x values. So we look at the x values, we don't worry about what it increases to or decreases to. Up to about 4 1/4. Now, there's another place where it starts increasing at about 9 up to positive infinity. Again, notice I'm only including the x values, and whenever we have two intervals, we union them together with a u. What's nice about that is it's decreasing in between 4.25 and 9. We'll always use parentheses instead of brackets because, for instance, at 9, it's neither increasing nor decreasing. That's where it's changing. Now, also, let's find some relative extrema. We have 2. Right here at the point roughly 4.25 comma, looks like about 50. We have what we call a relative or local maximum, because it's maximum to the points around it, or also we could say the function went from increasing to decreasing. That's a relative extrema. This is also a relative extrema, except it's not a relative max. We're at about 9, maybe negative 8. This is what we would call a relative minimum, or a local minimum, because it's minimum locally to the points around it. Or our function went from decreasing to increasing. Now these are points. So I know they look similar. These two are interval. These three are intervals up here, and these two are given as points. So make sure you can make that distinction. Now the other thing we're going to look for in this graph is concavity. We're going to look to see where it's concave up, and we're going to look to see where it's concave down, and then we'll check to see if there's any inflection points. Concave up means the graph opens upwards, like it is right here. Concave down means it opens downwards. So somewhere in here it switches. So let's just kind of pick a point. Maybe we say it happens about right there. So we need to identify that x value because that's where it switches. Now it's not quite 7. It's a little further than 6. So let's say that it's about, right there is about 6.75. That means our function is concave down from negative infinity up to 6.75. This is an interval, so I only pay attention to the x values. It's going to be concave up from 6.75 to infinity. This is important because when a function is concave up, it means we have an increasing rate of change. When it's concave down, it means we have a decreasing rate of change. If a graph changes concavity, that means we have what's called an inflection point. And it's roughly at about 6.75, 20. So what we have there is what we would call an inflection point. And we give that again as an ordered pair. So just as a reminder, these three are ordered pairs because they're a point. Up here, these are all our intervals for increasing or decreasing.